It seems that academia has, in some sense, given up on looking for a candidate model for how neurons may do computation. A model that does the cognitive functions in a flexible way like the brain does, but also is practical in neurons and also shows a lot of the phenomena that are associated. And you can tell this by the reduction of funding for things like this, and also the fact that we only have 5 minutes for this whole video. So I'm going to be skipping a lot and just giving you a taste. There are two predominant models of recognition today. One is Bayesian networks, and it's actually the most brain-like because it allows logic-type reasoning through priming through priors and expectation via likelihood. You have a way to say, oh, what am I expecting when I'm looking for a cat? And between both of those, you can actually perform logic, prefer to look for one thing over another. But the problem is, this is not connectionist. You can't build the model with theoretical neurons, and it's not scalable to large networks. The other type of model is neural networks, which all of them primarily do recognition by figuring out a set of weights and then multiplying the input through the set of weights. And it doesn't matter if it's deep or convolution or time, it's all through the same mechanism. These are much more scalable, but they don't have this brain-like priming or priors. And some people consider them connectionist, but they're only semi-connectionist. They're connectionist during recognition because you can have a neuron with weights and multiply through, but what you can't build with neurons is the whole rehearsal system that's needed to train these things. This model has quite a bit of hand waving to it, and I call this a gambling problem, which requires casino card dealers. And if you get only one thing from this talk, this is it. So let's briefly go over it. In a lifelike timeline, you would see a pattern learning. You see another pattern, learn it. Let's say bicycle, car, and then another type of bicycle, and you just kind of learn it as things come, unsorted. But the neural network models require carefully dealt training data. So a corresponding timeline for the same things that you would expect in a realistic timeline, well, you can see the first thing. But then when you see the second thing, you have to retrain the network with all the old and the new. So you have to store everything and then present them in a random way like a car dealer would. So everything that's stored gets in a deck and then it's presented. So it's dealt to the algorithm to learn, and then it's reshuffled, redealt again, and repeated. Now, the next pattern you're learning, the new pattern, and everything is reshuffled again from the beginning, dealt, reshuffled, and repeated to learn the new thing. If you now encounter another thing, well, you have to go back all the way, take all the patterns, rehearse them again, rebuild the new network in order to now know the new pattern. And this continues and continues to the size where this is too big for even a computer algorithm to learn as much as the brain is able to learn. So data in these neural networks must be carefully prepared and balanced. And the problem is neuroscientists don't implement this with neurons. And this is so important that you implement both the learning and the recognition through connectionist neuron plausible networks. Moreover, neither of the two models innately displays network-wide bursting. And you see that when you record neurons and you present something unexpected, you see a lot of neurons activate and then they come back down. And it's irrelevant of the type of organism or modality. Moreover, you don't see other cognitive phenomena such as difficulty with similarity, where it's easier to find something unique in a background that's very different, but it's harder if the background is very similar. And there's also these phenomena of asymmetry. And there's also phenomena of how uniform the background is. There's also a phenomena of speed-accuracy trade-off. If you're forced to make a quick decision, then the harder things, you're going to have more errors than the easier things. And again, neither of these two models model any of these effects inherently. So the goal is an innate model to minimize hand waving, don't have any implausible mechanisms, and have no extra parameters. So you want the model that shows the most amount of phenomena with the least amount of free parameters to try to fit the data. I present a model that uses presynaptic homeostatic-like regulatory feedback, where the weights are the likelihood average and the priors are determined by baseline of activity. So you have both the priors and the likelihood. This is a feed-forward feedback model, not a feed-forward like neural networks. I don't have much time to jump into details, so let me just run through how it works. If an input goes to output neurons, then those output neurons have to turn around back and feed back to the same input and modulate that input. That's part of the homeostasis and the regulation. Each input is regulated that way. So if another input goes to 4 cells, then it has to go back to those. But the beauty is you can intermesh this as much as you want, and the circuit will still function, which allows the flexibility. You can redraw this into a much simpler form. And so how does this model work? What I'm going to do is compare the neural network feed-forward models with this model. And as you see, the matrices are the same size. There's 2 outputs, 2 inputs. And so let's draw the nodes. They're both going to have the same inputs and outputs. So for this example, I want neuron YA to be active when only X is 1. That's the pattern of the likelihood. And neuron YB to be active when X1 and X2 are 1. And that's the likelihood of B. And since the weights can be the likelihood here, I can just put that into the matrix of weights. And so I put in the weights of neuron YA and YB. Let's obtain the feed-forward weight for these properties in a feed-forward neural network. And what you would have to do is take these patterns, deal, reshuffle, and repeat in order to get the weights, and then you get the feed-forward weights. Now, let's draw the network itself. In the feed-forward neural network, the weights are feed-forward, so you just put them in. I'm not going to write 1s and 0s. Instead, I'm going to draw yellow for active, black for inactive. And then I'm going to put this in as the input for the neural networks. They work by multiplying it through, so you get an immediate answer. And your dynamics, there isn't any. You get the answer going through. Now you can also put the other pattern, and you get the right answer for that. So now let's compare with the feed-forward feedback algorithm. And so the weights are feed-forward feedback. So if neuron YA gets a weight of 1 going into it, it has to have a weight of 1 going back. And now if the weight is 0, I'm just not going to draw a connection. Now neuron 2 has 2 inputs going to it, so it has to feed back and regulate those 2. And that's it. That's the model. Now the key here is it works iteratively during recognition. This is very counterintuitive, and this is why it's so difficult to bring this up as a model, because people are so used to the neural networks and not willing to look at other ideas. So information goes forward, then backwards in this model, forward, backwards. And I'm going to walk you through activation of 1, 1. That's going to be the stimulus. It's going to be constant throughout all the iterations. And so that goes into the inputs. And initially there's a big mismatch between the feedback and the feed forward because the inputs are new. So that boosts up the activation and makes initially both outputs burst and become active. And so then you see the dynamics going up for both the neurons. Then information feeds back down, but you'll notice that this input has twice as much inhibition as this. So it's going to get dialed down relative to this input. And then when information feeds back up, this neuron is much more dependent on this input than this neuron, so the neurons start to separate. And this affects neuron YA much more than YB, and you start seeing a separation in the dynamics. And this continues iteratively and continues to separate and continues to separate until you get the same answer for the recognition, except you now didn't need to calculate any of the feed-forward weights. You used the likelihoods, and so you have more intuition of what's going on, and you didn't have to go through the rehearsal process. So now I want to show you a more realistic learning that current neural networks can't do. And so I'm taking the iris data set. These are 3 different types of flowers with 4 different types of features. And I take it because it's the simplest thing possible. I take all the data of just 2 flowers, and I'm going to train a network on only those 2 flowers. And then I can test the accuracy on it, and it does really well. Then I'm going to designate a new neuron for the 3rd flower, and then I'm going to present only the data for that 3rd flower, train that, and that's it. Right? So there's no rehearsal of any other flowers. And then I can retest the network, and it shows the exact same performance of whether I trained it with rehearsal or without, or it doesn't matter what the order was. Ultimately, as long as all the flowers were presented, it learns the same thing. Now, this model also shows network-wide bursting, as you saw in the demonstration, but here we trained it on the digits of the post office, and we presented digit 1. And you can see the dynamics for a recognition example of the digit 1. You also see brain-like effects. And so we trained it on 26 patterns, and then we sorted all the patterns out based on their similarity. How many number of features overlap or are different. And we did this through a convolution-like field, but we looked at every possible feature, and then we looked at the differences. Then we present the 2 patterns, the first one, then flip it to the second one and see how long it takes to recognize. And when you look at the graph, the more similar the 2 patterns are, the harder it is to recognize. And it also shows some phenomena of asymmetry, which I don't have the time to show, but that's that curious dot that's out there. This also represents a speed accuracy trade-off. So if you have to make a fixed decision at a fixed amount of time, well, the harder ones you will have more error in, and the easier ones you won't. And if you did this with feed-forward network, you have no difference with similarity. It all takes the same amount of time because you multiply through y equals wx, and so you don't have any speed accuracy trade-off. You would have to build mechanisms to try to emulate this. You're not going to get this out of the native recognition model. So to summarize, the brain, not known what method. The Bayesian network uses Bayes rules, and the neural networks use the feed-forward, and the homeostatic regulatory network uses input-output regulation during recognition. The neural network is only half connectionist. It doesn't have any priors, but the Bayesian does. It doesn't have any likelihoods, but the Bayesian does, but so does the regulatory feedback. And the reason why Bayesian is really hard is you have to explicitly calculate distribution, which is a mathematical construct, and that makes it unscalable and really hard to use the Bayesian networks unless you're using very small amounts. But in the feed-forward network, these distributions are still there, but they're hidden in the rehearsal and during training. You don't have access to them, but they're determined by how you presented the rehearsal, which is why these networks are so sensitive to the rehearsal. And in this method, it's estimated during recognition. So you never calculate the distributions until you are recognizing, when you have all the information of what you've learned plus the pattern that you want to recognize, and then you determine the estimate of what is it best likely going to fit. So this is why it has so much more flexibility. And that allows the easier learning and modular update, where I can learn the 3rd flower whenever I want. The feed-forward feedback part of the mechanism of estimating is what gives this bursting of going up and down, and it gives the cognitive phenomena. I feel people are either stuck on the feed-forward network or the Bayesian network, or there's now a push to do both at once. But neither method get over the computational problems. So everything needs to be looked at through a multidisciplinary view. And I really hope academia will start looking at this and start funding these types of models and to move forward the neuroscience. Thank you.